Time to solve the first equilibrium problem. You can see from the picture, we kind of call these hanging weight problems. Now, going through the procedure, step one is to sketch the situation. A sketch was already given. I'm going to redraw it just so we can analyze it a little further. So here's the wall and a ceiling. And let's see what we had. This was marked as 50 kilograms, 52 degrees, ropes A and B. So that's the sketch. So step one is really to isolate an object once we have this sketch. So isolating an object means let's pick an object that all the forces we care about are going to act on. So usually when people look at these, the first thing they decide is, oh, I got to isolate this ball or the weight because that's the thing. Let's see what would happen if we isolated the weight. So free body diagram about the weight. For these problems, we're going to just kind of draw a set of axes, and the object we isolate is going in the middle. For hanging weight problems, this is the best way to approach them. So this is the 50 kilogram ball. Now, the rules say we only draw forces that directly act on the ball. So what forces directly touch the ball? When we see a rope touching the ball, we didn't call it. It must act up. Tension in the rope has to act up. Ropes don't push on things. There's one force. The other force that directly touches the ball is the weight of the ball. 50 kilograms is a mass. It can't go in a force picture. So how do we draw the weight? First, weight acts down, and the formula is weight equals mg. 50 kilograms times 9.80 meters per second squared. The weight of the ball is 490 newtons. This is very important. You must use weight equals mg, not just m. So there are no other forces acting on the ball. Notice A and B are not in the picture. They don't directly touch the ball. So the only thing this tells us is something we might have been able to guess. If we look, there are only two forces on the ball, the rope C and the weight W. The only thing that can mean is if we sum the forces in the y direction and set them to 0, because that's equilibrium, C minus W equals 0, or C equals W, or the tension in the rope is 490 newtons. That didn't really tell us anything that we couldn't have figured out by looking. So the question is, what do we isolate? In these pictures, it's kind of a little trick. We isolate the intersection, or we can call it the knot. We always isolate the knot. These forces, as we mentioned in the reading, are called concurrent. They intersect at one point, so we are really isolating the point of intersection. So if we isolate the knot, we'll draw a free body diagram about the knot. Here are our axes, x and y. Let's draw forces. Forces leave the knot. Forces don't enter a knot. Here's A. We want this angle. This angle is 52 degrees. You have to know a little bit of geometry. Really the way it looks is we have this line bisecting two parallel lines. And the big long math rule. When you have a bisector bisecting two parallel lines, the alternate interior angles are equal. You could say that, or just call it a Z. It's the Z rule. This whole thing kind of looks like a Z. Angles inside a Z are the same. Easy way to think about it. 52. Here is B along the negative x-axis. And now, just to make sure we split some hairs on this, this is not the weight of the ball going down. This is the tension in rope C. The ball doesn't touch the knot, the rope does. But since we know they're equivalent, that's 490 newtons. Remember, that is the tension in rope C. This is a good free body diagram. Step 1. The next step is to resolve forces on the diagram into components. I tend to go around in a circle starting at quadrant 1. So A needs to be resolved into components. We do it the same way as we have always done. Hypotenuse, included angle, adjacent side. All because this isn't a number doesn't mean we approach it differently. This x component is A cos 52. The y component is A sine 52. B does not have to be resolved into components. It's on axis, nor does the 490 newtons. Once we have a good free body diagram, we can start writing equations. How do we want to do this? The appropriate equations are: sum of the forces in the x direction are 0, sum of the forces in the y direction are 0. Notice how I'm not writing these vertically. I'm writing them next to each other because we are going to have simultaneous equations. And we don't want to make more out of this equation. The left side simply says, look along the x-axis, add things you find according to algebraic sign. So let's find things that act in positive x. We have 1, A cos 52 degrees, minus what we have in negative x, B. Notice I am not using the standard angle of B cosine 180. These problems are much easier if you use the reference angles. Don't mix up double negativing by putting something like minus B cos 180. That would be very bad. I would use what you have on the picture. They're the only two forces in the x, equals 0. Now we can do the same for the y. A sine 52 minus 490 newtons equals 0. The physics is now done. The only thing left is math. So we have two equations and two unknowns. We have to find the easiest one to work with first. Since the y equation only has one unknown, we'll solve that first. A sine 52 equals 490 newtons. So that says A is 490 newtons over the sine of 52 degrees, which is 622 newtons. That is the tension in rope A. Well, to get the tension in rope B, we're going to substitute. B equals A times the cosine of 52 degrees. Substitute that in over here, and when you do, you will end up with B equal 383 newtons. And those are the two answers. A 622 newtons, B 383. A very quick check. None of the numbers can be negative. These are magnitudes of forces. These magnitudes cannot be negative. So that's a very, very brief check. That's the solution of this problem.